And thank you for letting me speak here. It's really an interesting conference, so thank you. So as said, I would like to present my work on method of moments for stochastic development regression. The stochastic development regression is a model that I introduced at an IPMI paper this year, so that is not new. The new thing is how we do parameter inference in this model. And for that we will use this method of moments, which is a Euclidean method that has been used a lot in statistics. So first of all, what is this stochastic development regression? So our goal is to model relationships between Euclidean covariate variables and a manifold valued response. So this has been done of a lot of people, like geodesic regression, kernel-based methods. But what we want to do is to define an intrinsic model that does not do any linearization of the manifold. We would like to have a model which includes several covariate variables, and the way we do this is by defining the model by stochastic processes, and therefore it can also model non-geodesic relationships between these two variables. So the idea is that we present a Euclidean regression model on a Euclidean space, and then we take this map, which is called stochastic development, and define stochastic processes on the manifold. So by doing this, we introduce a natural time variable into the model, which I will come back to in a minute. Okay. So first of all, what does this stochastic development mean? What is the map that we map Euclidean stochastic processes to the manifold? And it is by this stochastic development, and the stochastic development goes through a space called the frame bundle. So for those of you who are not aware of this frame bundle space, if we have a manifold M with some dimension D and a connection which could be the Levita connection that I've been using, then a point on the frame bundle is just a tuple of a point on the manifold Q, and then an ordered basis for the tangent space at that point Q. Here, an ordered basis is also called a frame, and hence the name frame bundle space. So I see the frame bundle as stacking the manifold on top of each other, and if through the fibers of the frame bundle, you go through different bases of the tangent space, and you move horizontally. You kind of fix a frame, and then move along the manifold. And when I say fix a frame, means that if you move along the manifold, you are kind of taking the frame and parallel transporting it along when you're walking. So that also means that we can split the tangent space of the frame bundle up into a horizontal part, meaning moving on the manifold, and on the vertical part, where you are changing the basis of the tangent space. So what we wanted to do was to define a stochastic process on a Euclidean space and then transport it to the manifold. And when you consider a stochastic process on this frame bundle here, at each time point it would be a point on the manifold and a frame for the tangent space. But the thing is that for our stochastic process, we don't want this frame to change, because we want the covariance to be the same at each time point, and this frame nu is related to the covariance of our stochastic process. So therefore we only want to move horizontally in this space. Okay, so how can we define this stochastic process on the frame bundle? So if we are given a stochastic process in a Euclidean space Rm, and we have a basis for the horizontal subspace where we wanted to move on the frame bundle, then a stochastic process on the frame bundle ut can be defined by this stochastic differential equation. This circle here means that it is a Stratonovich stochastic differential equation, and that is just another way of doing stochastic integrals. So instead of taking the left part of the intervals, function value there, you take an average and do that. And in stochastic theory, this is not the same. So this basically just means that the amount that you are walking in the ith dimension of the Euclidean space, you walk that in the ith direction of the horizontal basis. Okay, so this, if we solve this by a numerical optimization procedure, then we get a stochastic process on the frame bundle. And we can project this stochastic process onto the manifold by just, at each time point, we throw away the basis. Because this UT was, at each time point, a point on the manifold and a frame. So by just throwing away the frame, we then get a stochastic process on the manifold. Okay, but what does this have to relate to the regression model that I want to define? Well, the idea is that we would like to take a Euclidean linear regression model, define it as a stochastic process, and then transport it to the manifold to get a response relation. So here, the model is we take n noisy observations of the response variable on the manifold. We consider xi as being the covariate vector, so we have m covariate variables in this case. Then, because we have this time evolution, we say that we actually have a whole evolution of covariates. So we introduce these XIT processes, which will be a Brownian bridge at a initial point, and which ends in our covariate variables. So you could maybe say that, okay, because we have this time variable in our model, it could also be used for longitudinal data, where you have several observations for a person over time. And then these XITs would just model this relationship with the covariate, or the time evolution of the covariate variables. But in this case, we only measure stochastic, and hence we model these as Brownian bridges. So the stochastic process that we want to transport to the manifold is then given by this stochastic differential equation, where we see that this is actually almost like a linear regression. We have an intercept here, which is a fixed drift with some parameter alpha. We have a covariate dependency, where we have W as being the parameter matrix for the covariates. And then we have some IID random noise, which is modeled in this case by just a Brownian motion. So this defines a linear regression model stochastically on the Euclidean space. And what we then do is to model our observations as being the endpoint of the stochastic development projected to the manifold based on some starting points on the frame bundle of these ZIT processes. So we define our ZITs here in the Euclidean space. We make the stochastic development to the frame bundle here, and then we project those down to the manifold to get the dependency to the response variables. Okay, and then we say at the endpoint here we also measure some additive noise, where this additive noise is just normally distributed, 0 tau squared noise. So this is an additive noise in the Euclidean space, so this could actually pull our observations to the ambient space. And we put this noise on our model because we're seeing that when you are doing or having brain images or whatever, you can measure them with some bias on them, and what you see is basically not a brain. So that is why we introduce this noise. Okay, so that was kind of the idea about the model. So it's just, we use these stochastic processes to relate the covariate space to the response space. And we have a lot of parameters that we like to find, estimate, which is the alpha, the W vector, the initial Y0 on the frame bundle, and the new 0 on the frame bundle, and then this noise variance parameter here. Okay, so we would like to introduce this method of moments for doing this inference. And the method of moments is a procedure where you take some methods or some moments that you know, and then you match them to the given or some simulated data. So in this case, we have our additive noise, which we know is normally distributed with mean 0 and tau squared variance. So you say, okay, we know these three conditions, and we would like to match those. and then find the minimum or the parameters that are simulating observations that gives these 3 moments back. And notice here that instead of estimating the W matrix and nu 0, the initial frame, like separately, we do it simultaneously because they are related to each other. Okay, so the objective function that I'm trying to minimize is then given by n, where n is the number of observations, predicted values of this additive noise, and here d is the dimensions, because for each landmark, for example, we have the mean should be 0 for each landmark. Then we have the independence of the covariate, which is approximated by this mean here, and then we have the second moment of the residuals here approximated by this sum, average sum. Okay, so in a Euclidean case, we know that method of moments has or provides consistent but potentially biased parameters. So in order to see whether this is the case in my procedure here, I did some experiments on just one landmark. So in these examples I will show here, I have a manifold of landmarks, which is defined in the LDDMM case that Alain was introducing earlier. So here I've done some for just one landmark, meaning that we are in a totally Euclidean space, so everything should work here. So what I see is that here we have the true parameters for my model. Here I did a really simple model where I didn't include error or drift, and we see that they could figure out how to find the W tilde parameter and the initial point. Here I added some noise, and it seems like there is some sort of bias in this parameter, which was also the case for a Euclidean method of moments, so I have to figure out why is this. And then the really interesting thing is that if we introduce drift, we see that there is a relationship between the initial point here and the drift. So this means that I've only included one covariate variable in this case, but you can see here that y0 is kind of put too high, and then we don't have to drift that long on the manifold, which makes sense. So these, you could, maybe I should have done some simultaneous estimation of these 2 parameters, but yeah, that is something I have to work on. Okay, so I did some more landmarks and more things to see if it actually makes sense what it's doing. So here I estimated the tilde W parameter, the initial frame, and the parameters for the covariate variables, and the initial point where I start my stochastic processes from on the manifold. I have just made circles of 8 landmarks here. The red one is the true, and the green one is my estimated, and you can see there are some red arrows behind my green ones, and then the blue one was my initial value. So it seems like it is able to find the real parameters. And then here I made some estimations of the initial value, y0, and this is the distribution of 100 simulated samples where I've estimated the initial value, and it looks kind of nice. I also did it for 200 observations in each sample, and the distribution got narrower, so it seems like it's working. And then just for some eye candy, I don't know if it's eye candy, but here I did some 30 landmarks on a circle, and it still captures the right parameters quite well. So yes, I see that Xavier is standing, so summary and future work. So I've introduced an intrinsic regression model on the manifold, which does not do any sort of linearization. It can include several covariate variables, but there are some bias in the variance parameter, and I have to do some simultaneous estimation of the drift and the initial point. And then I would also like to try this on longitudinal data, because we have this time variable, which will, it would be pretty obvious to try it on that. So, yeah, thanks.
Thank you for the nice talk. Are there questions? Yes?
Thank you. Would it be possible to extend this to the case where the covariate is manifold valued by having a stochastic development for the covariate X as well?
Yeah. Yeah, I think it would. Like, I haven't looked at the stochastic development map when you're going from one manifold to another, but I'm pretty sure that it is possible to do that. So it would just be changing that map for this case in this model, and then you would get. So yeah, I'm pretty sure it would.
Great, thanks.
Other questions? So I've got one of the question. I think the question is small, but the answer might be difficult. So far you assume that you have some isotropic noise, something like that. So do you think you can estimate anisotropic noise as well?
Well, yes.
And the related question is, how much data do you think you need to do that?
That's a good question. But so the anisotropic noise I can do by this, so the W and the frame that I develop my stochastic process with is determining what sort of distribution I get on the manifold. So by changing the W matrix, because I always keep the basis for the stochastic development as an orthonormal basis to get the isotropic distribution. So by changing the W matrix for the covariate variables, I would get an anisotropic distribution there.
But to estimate it, there's no. So far I mean, you're estimating just one parameter, right? For the variance, or you're estimating the full.
So I estimate one parameter for the noise variance.
Yeah. Oh, that's the noise variance. Okay.
Yes, exactly. Yeah. So this variance is just one parameter, which is just the additive.
And if you put something which is not, well, if you want to estimate the full covariance here.
For the additive noise?
Yeah. Maybe for GSI in 2 years.
Yeah, maybe. I don't know yet. Yeah.
Okay.
Yes.
Thank you very much.